The sun is alive with power. Massive bursts of energy, called solar flares, can supercharge Earth's upper atmosphere, disrupt radio signals, and even threaten satellites and astronauts. But recent research has revealed something that will blow your mind. Solar flares are hotter than scientists ever imagined, and the secret lies in a surprising temperature split between the sun's particles. Solar flares are sudden bursts of magnetic energy on the sun's surface. Imagine the sun turning the volume all the way up, sending streams of superheated plasma into space. For decades, scientists have been puzzled by the strange behavior of these flares. Certain spectral fingerprints, bright lines in ultraviolet and X-ray light, look too wide to make sense. Physicists called it a mystery since the 1970s. Now, thanks to a team at the University of St. Andrews led by Alexander Russell, we finally have an answer. Here's the key. The sun's plasma is made of electrons, light, negatively charged particles, and ions, heavier positively charged particles like iron and calcium. Earlier models assumed electrons and ions share heat evenly. But Russell's team discovered something amazing. During the early stages of a flare, ions get much hotter than electrons, about 6.5 times hotter, reaching over 60 million degrees Kelvin. This difference explains the mysterious broad spectral lines without needing to invoke chaotic turbulence. Simply put, the ions are so hot that their motion spreads the light across a wider range of wavelengths. It's like the ions are having a fever, while the electrons are just sitting there sipping tea. This discovery isn't just about bragging rights, it reshapes how we understand space weather. Solar flares influence everything from radio communication to satellite safety, and even astronauts in space. If ions heat first, the energy transport, shock waves, and particle acceleration are all different than we previously thought. That changes predictions for solar storms and how we protect Earth's technology from their effects. Russell and his team combined observations, theory, and computer simulations to tackle this decades-old problem. They applied a well-known process from near-Earth space called magnetic reconnection, where stressed magnetic fields snap and release energy, to solar flares. In the sun's upper atmosphere, where plasma density is low, ions stay hotter than electrons for minutes. This creates the unusually broad emission lines scientists had seen for 50 years. It's an elegant solution, nothing revolutionary, just a universal law applied in the right place. This insight gives scientists a roadmap for future solar flare observations. By comparing spectral lines from different ions with electron-sensitive diagnostics, we can test the 6.5:1 temperature ratio directly. It also encourages models to treat ions and electrons separately in the first crucial minutes of a flare, instead of forcing them to share a single temperature. In short, understanding the hottest particles in the sun helps us better predict space weather and protect our technology and maybe even life on Earth from the sun's fury. Solar flares are more than dazzling light shows, they are the sun at full power, and now we know that ions take the heat first, reaching temperatures hotter than we ever imagined. This breakthrough finally solves a 50-year-old astrophysics mystery and brings us one step closer to decoding the sun's most powerful moments.